The universe does not announce its intentions. It moves in silence. Beyond the orbit of Neptune, past the frozen boundary of the known planets, lies a vast spherical shell of icy debris, a distant reservoir left over from the birth of the solar system. In that darkness, untouched for billions of years, objects drift in slow motion around the sun, and sometimes one falls inward. When C-2023A3 Schinchin Adios appeared in the sky, it was not merely a spectacle. It was a messenger from deep time. Comets are older than Earth's oceans, older than mountains, older than life itself. They are fragments of the original cloud of gas and dust that collapsed to form the Sun 4.6 billion years ago. When gravity pulled that cloud inward, most of the material became the Sun. Some formed planets. The frozen debris were scattered outward, forming distant reservoirs of ice. C-2023A3 began its journey in that frozen frontier. For billions of years it remained in darkness, a nucleus of ice and rock perhaps only a few kilometers across. Then gravity intervened. A passing star, a subtle gravitational tug, a disturbance in the cosmic balance, and its orbit shifted. It began to fall. As it traveled inward, sunlight awakened it. Ice that had been stable for eons began to sublimate. Gas erupted from its surface. Dust was released into space. A glowing coma formed around its nucleus. Solar winds stretched that material into a luminous tail that could span millions of kilometers. From Earth, it appeared as a streak of light. But its true significance was invisible. Every comet is a time capsule. Locked inside its frozen core are pristine materials from the early solar system: water, ice, carbon compounds, nitrogen-based molecules. These materials have remained largely unchanged since the dawn of planetary formation. In a sense, a comet is a fossil. By studying the light reflected and emitted from a comet, spectroscopy reveals its chemical composition. Each molecule absorbs and emits specific wavelengths. Those wavelengths form a pattern, a fingerprint written in light. Through this method, comets have revealed the presence of water, methane, ammonia, carbon monoxide, and more complex organic molecules, the building blocks of life. Life on Earth depends on carbon chemistry. Carbon's unique ability to form long chains and complex structures makes biology possible. The presence of complex carbon molecules inside comets suggests that prebiotic chemistry is not rare, it is cosmic. 4 billion years ago, Earth was under constant bombardment. Asteroids and comets struck its surface in a period known as the Late Heavy Bombardment. Those impacts delivered enormous quantities of water and organic compounds. Oceans may have formed from countless icy visitors. The chemistry of life may have been delivered from space. If that is true, then Earth's biology has extraterrestrial roots. The discovery of interstellar objects like Oumuamua and Tud Borisov changed the understanding of cosmic isolation. These objects prove that material can travel between star systems. Planetary systems are not sealed. When stars form in clusters, gravitational interactions can eject comets into interstellar space. Those objects wander the galaxy for millions or even billions of years. Eventually, some may enter another star system. This exchange suggests that chemistry itself may be migratory. The galaxy, the Milky Way, contains hundreds of billions of stars. If even a fraction of those stars possess cometary reservoirs, then interstellar space is filled with icy wanderers. Over cosmic timescales, material mixing becomes inevitable. The implications are profound. If water and organic molecules are distributed throughout the galaxy by comets, then the ingredients for life may be common. The rarity of life would then depend not on chemistry, but on stability, the right conditions persisting long enough for complexity to emerge. C-2023A3 serves as a reminder of this larger story. It is not simply a visitor lighting up the night sky. It is evidence that the solar system remains connected to its ancient past. It demonstrates that the processes of formation, ejection, and return continue even now. Comets are dynamic participants in cosmic evolution. Their orbits can be elliptical, returning periodically. Others follow long, elongated paths that take tens of thousands of years to complete. Some follow hyperbolic trajectories, meaning they are not gravitationally bound. Visitors from beyond. Each orbit tells a story of gravitational encounters and distant perturbations. Each comet carries within it a chemical archive. When sunlight strikes a comet and creates its luminous tail, it is not merely beauty, it is revelation. The glowing gases reveal composition. The dust reveals structure. The isotopic ratios reveal origin. Science decodes what the eye cannot see. And what emerges is a universe rich in complexity. The atoms within a comet were forged inside ancient stars. Carbon formed in stellar cores. Oxygen emerged from nuclear fusion. Nitrogen arose from explosive stellar deaths. Those atoms drifted through space before becoming part of a molecular cloud. From that cloud came the sun. From that cloud came the Earth. From that cloud came life. And from that cloud came the comet now streaking across the sky. In that sense, the appearance of C-2023A3 is a reminder of continuity. The boundaries between stars and planets are not rigid. Matter cycles endlessly. Atoms are recycled across cosmic generations. The universe is not static, it evolves. And within that evolution lies the possibility that life itself is not confined to a single world. If comets carry water and organic molecules to young planets, then similar processes may be unfolding elsewhere, around distant stars, on distant worlds, beneath distant skies. The lesson is subtle yet transformative. The appearance of a comet is not merely an astronomical event. It is a glimpse into the origin of oceans, the chemistry of biology, and the interconnectedness of star systems. It suggests that life may not be an isolated miracle. It may be part of a larger cosmic pattern. And as that comet continues its journey, arcing around the sun and retreating once more into the outer darkness, it leaves behind more than a fading tail of light. It leaves a question suspended in space. If the ingredients of life are everywhere, how many worlds have already begun the experiment? Space is not empty. It only appears that way. Between the stars lies a thin ocean of dust gas, frozen debris, the raw material of creation. And when an object like C-2023A3 Sachinshan 8 emerges from the depths of the solar system, it carries within it a chemical record older than Earth itself. Every comet is a relic. Before planets formed, before oceans gathered, before continents hardened, there was a spinning cloud of hydrogen, helium, carbon, nitrogen, oxygen, the debris of dead stars. Gravity pulled that cloud inward, pressure ignited the sun. The leftovers became planets, moons, asteroids, and comets. Comets are the leftovers. They are frozen time capsules, preserved in the deep freeze beyond Neptune, largely untouched for billions of years. When one falls inward toward the sun, sunlight awakens it. Ice sublimates, gas erupts, a glowing coma forms. A tail stretches millions of kilometers across space. But the true story is invisible. Spectroscopy, the science of breaking light into its component wavelengths, allows the decoding of a comet's chemistry. Each element leaves a fingerprint in light. Carbon glows at specific frequencies. Oxygen reveals itself in faint emission lines. Complex organic molecules whisper through subtle signatures. When light from a comet is analyzed, the universe is speaking in code. The chemistry found inside comets is not random. Water ice is common. Carbon monoxide, methane, ammonia, all are present. More astonishing are complex organics, long carbon chains, precursors to amino acids, the scaffolding of life. Life requires complexity, complexity requires chemistry. Chemistry requires stars. Every carbon atom in a comet was forged inside a star that died billions of years ago. That star exploded, scattering enriched material across space. New stars formed from that debris. New planetary systems emerged. Comets condensed from the leftovers. In that sense, a comet is stardust in motion. The presence of organic molecules inside comets changes the equation of life. For centuries, life was assumed to be rare, perhaps unique. But if organic chemistry emerges naturally wherever stars are born, then the building blocks of biology are not rare, they are cosmic. The early Earth was hostile. Molten rock, constant bombardment, a toxic atmosphere, yet within a few 100 million years life appeared. That speed is puzzling. It suggests that either life forms easily, or it arrived pre-packaged. The late heavy bombardment period showered Earth with comets and asteroids. Each impact delivered water and organics. Oceans may have formed from countless icy visitors. The chemistry necessary for life may have been delivered from space. If so, Earth is not a biological miracle. It is a chemical inevitability. Objects like Oumuamua and Two-Eyed Borisov revealed something profound: planetary systems exchange material. They are not sealed containers. When stars form in clusters, gravitational interactions fling comets outward at enormous speeds. Some are ejected into interstellar space. Those frozen wanderers drift for millions, sometimes billions, of years. Eventually, one may encounter another star. If organic chemistry can survive that journey, shielded inside rock and ice, then molecular seeds could spread across the galaxy. This concept, known as panspermia, does not require advanced civilizations. It requires only physics. Radiation in space is intense. Ultraviolet light shatters molecules. Cosmic rays break chemical bonds. But deep inside a comet's nucleus, protected by layers of ice and dust, complex molecules can endure. Laboratory experiments on Earth have shown that amino acids can survive simulated space conditions when shielded. The galaxy may be performing a vast, slow experiment in chemical distribution. Consider the scale. The Milky Way contains hundreds of billions of stars. Many possess planets. Many of those planets reside in habitable zones where liquid water could exist. Around those stars, cometary clouds likely form, similar to the Oort clouds surrounding the Sun. Each system occasionally ejects debris. Over billions of years, interstellar space becomes populated with wandering ice fragments, trillions upon trillions of them. The discovery rate of interstellar objects is increasing as telescopes become more sensitive. Facilities like the Pan-STARRS and the upcoming Vera-C Rubin Observatory are designed to scan the sky continuously, detecting faint moving objects. Each detection is a data point in a much larger narrative. Chemistry does not care about borders. Gravity does not respect ownership. The galaxy is porous. When analyzing cometary spectra, scientists look for ratios, deuterium to hydrogen, isotopic signatures, unusual abundances. These ratios reveal origins. Some comets contain water slightly different from Earth's oceans, suggesting multiple sources contributed to terrestrial water. This implies mixing. Earth's oceans may be a blended recipe from countless cosmic deliveries. Complex organic molecules such as glycine, the simplest amino acid, have already been detected in cometary material. The Rosetta mission to Comet 67P revealed a surprisingly rich chemistry. If one comet can contain such diversity, imagine billions across the galaxy. The leap from organic molecules to living cells is immense. Yet chemistry naturally trends toward complexity under the right conditions. Given energy sources, sunlight, hydrothermal vents, electrical discharges, molecules self-organize. Life may not be an accident, it may be a phase transition. When conditions cross a threshold of complexity, chemistry becomes biology. An object like C2023A3 is more than a spectacle in the night sky. It is a messenger carrying evidence that the ingredients for life are widespread. It reinforces a pattern already emerging from exoplanet discoveries. Planets are common. Water is common. Organic chemistry is common. The rare element may not be chemistry. It may be time. Civilizations require stability for billions of years. Impacts must decline. Climate must stabilize. Evolution must progress from microbes to intelligence. But at the molecular level, the universe seems eager. The lesson embedded in cometary ice is simple yet profound. The same atoms that compose living cells are forged in stars and distributed across galaxies. No boundary prevents them from traveling. Interstellar objects demonstrate that material exchange is real. Chemistry is migratory. Planetary systems are not isolated experiments. They are participants in a galactic network. Somewhere, on a distant world orbiting a faint red star, icy bodies may be delivering water and organics at this very moment. Oceans may be forming. Complex chemistry may be stirring. And perhaps billions of years from now, intelligence may look up at its own sky, watching a bright comet streak across the darkness, and wonder the same question. Is life local or universal? The answer may already be frozen in ice, traveling silently between the stars. The universe is not built in isolation. Stars are born together. Inside vast molecular clouds, cold, dark regions of gas spanning dozens of light years, gravity begins its quiet work. Over time, clumps of gas collapse. Temperatures rise. Nuclear fusion ignites. A cluster of stars is born almost simultaneously, like sparks from the same cosmic flame. The Sun was not born alone. 4.5 billion years ago, it emerged within such a stellar nursery, surrounded by sibling stars, each forming its own planets, moons, asteroids, and comets. In those early days, the solar system was not a calm, orderly place. It was crowded, and in crowded neighborhoods, encounters are inevitable. When young stars orbit within clusters, gravitational interactions occur frequently. A close pass between two stars can disturb the outer regions of their planetary systems. Comets, loosely bound and distant, are especially vulnerable. A subtle gravitational nudge can fling them outward at enormous speeds. Some are cast into deep interstellar space. Others are redirected inward toward their own stars. This process transforms planetary systems into dynamic engines of exchange. The discovery of interstellar objects such as Oumuamua and Tuig-Borisov provided direct evidence of this mechanism. These objects did not originate in the solar system. Their hyperbolic trajectories proved they were not gravitationally bound to the Sun. They were wanderers from elsewhere. Each interstellar visitor implies countless others drifting unseen. For every object detected, many more pass unnoticed, too small, too faint, too distant. The galaxy is filled with debris from planetary formation. Within the Milky Way, stars orbit the galactic center at hundreds of kilometers per second. Over millions of years, their paths weave and cross. Although collisions between stars are rare, gravitational influences extend far beyond visible boundaries. Outer cometary clouds, like the theoretical Oort clouds surrounding the Sun, are vast and fragile. A passing star does not need to collide to cause disruption. Its gravity alone can perturb distant objects. These perturbations act like cosmic slingshots. Some comets are accelerated enough to escape entirely. Others are captured by neighboring systems. Over billions of years, this slow exchange becomes significant. Planetary systems are not sealed ecosystems. They are participants in a galactic circulation system. This realization reshapes the concept of origin. If comets can travel between stars, then material from one system can become part of another. Water formed around one star may eventually rain down on a planet orbiting another. Organic molecules synthesized in one region of the galaxy may seed chemistry elsewhere. The boundaries between home and foreign dissolve. Consider the scale of time involved. A comet ejected from a young star cluster may drift for hundreds of millions of years before encountering another system. During that journey, it travels through near-perfect vacuum. Exposed to cosmic radiation, its surface may erode, but its interior remains shielded, preserving frozen chemistry. Eventually, gravity captures it. If its trajectory intersects a young planet, impact becomes possible. The implications are staggering. Life on Earth may not represent a completely local phenomenon. The building blocks of biology may have origins that predate the solar system itself. They may have been assembled in distant stellar nurseries long before the sun ignited. In this view, biology becomes a galactic story. An object like C2023A3 as Sochin LS serves as a reminder of this dynamic exchange. Even if bound to the sun, it represents the same processes that operate across the galaxy: formation, perturbation, migration. The solar system itself has likely captured material from other stars in its distant past. Some objects in the outer regions may not have formed here at all. Simulations of early stellar clusters suggest that capture events are not only possible but probable. The early solar system was embedded in a dense environment. Stellar siblings passed within a few light years, close enough to disturb outer cometary clouds. Each close encounter was a moment of gravitational negotiation. Matter was traded. Orbits were reshaped. Chaos gradually gave way to stability as the sun drifted away from its birth cluster. Over time, the solar system settled into relative calm, but the evidence of its chaotic youth remains preserved in the eccentric orbits of distant objects. This dynamic history teaches a fundamental lesson: stability is temporary. On cosmic timescales, systems evolve through interaction. Isolation is the exception, not the rule. The exchange of material between stars may also explain certain isotopic anomalies found in meteorites. Some isotopes present in early solar system materials suggest contamination from nearby supernova. Exploding stars may have enriched the forming sun with heavy elements. This means the solar system began with inherited complexity. It was shaped not only by its own collapse but by the deaths of neighboring stars. The same pattern likely repeats across the galaxy. Star formation is communal. Planet formation is universal. Gravitational scattering is inevitable. When observing the night sky, each star represents not just a distant sun but a potential source of wandering debris. The detection of more interstellar objects is expected as observational technology improves. Facilities like the Vera C. Rubin Observatory will scan the sky continuously, identifying faint moving points of light. Each detection will refine estimates of how common these wanderers are. Preliminary models suggest that trillions of interstellar objects may exist in the Milky Way at any given time. Trillions. This transforms the perception of space from emptiness to quiet abundance. If chemistry travels, then possibility travels. If possibility travels, then life may not be confined. The galaxy becomes less like a collection of isolated islands and more like an ocean with drifting seeds, carried by gravitational currents instead of wind. The birth of stars in clusters, the scattering of comets, the exchange of material. These processes are not rare anomalies. They are fundamental to cosmic evolution. The universe favors interaction, and through interaction, complexity increases. The story told by Part 3 is not one of collision and destruction alone. It is one of connection. Stars influence one another. Systems overlap. Matter migrates. And within that migration lies the profound realization that the ingredients of life may not belong to any single world. They may belong to the galaxy itself. The question is not whether planets exist. That question has already been answered. When the first exoplanets were discovered in the 1990s, they shattered a centuries-old assumption that the solar system might be unique. Since then, thousands of confirmed worlds have been cataloged. Gas giants larger than Jupiter, rocky planets slightly bigger than Earth, and strange hybrids unlike anything orbiting the Sun. Missions such as Kepler Space Telescope and TESS revealed something extraordinary. Planets are common. On average, there may be more planets than stars in the Milky Way. This changes the equation. If stars are numerous and planets are abundant, then the environments where life could potentially emerge multiply dramatically. But abundance alone does not guarantee biology. Conditions matter. Life, as understood on Earth, requires liquid water, a stable energy source, and complex chemistry. These requirements define what astronomers call the habitable zone, the region around a star where temperatures allow water to remain liquid on a planet's surface. But the habitable zone is not a guarantee. A planet may orbit in the right region yet lack an atmosphere. It may have water but no magnetic field, leaving it exposed to stellar radiation. It may have oceans but no geological activity to recycle nutrients. Habitability is a delicate balance. Yet observations reveal that rocky planets in habitable zones are not rare. Statistical analysis of Kepler data suggests billions of potentially Earth-sized worlds may exist in the galaxy. Billions. The discovery of objects like CVA 2023A3 Sachinshan Atlas adds another dimension to this equation. If comets distribute water and organic molecules widely, then young planets forming in these habitable zones may not begin chemically barren. They may be seeded. Probability becomes the central concept. In the 1960s, astronomer Frank Drake introduced a framework known as the Drake equation, a method of estimating the number of communicative civilizations in the galaxy. The equation breaks the problem into factors: star formation rates, fraction of stars with planets, number of habitable planets per system, probability of life emerging, probability of intelligence evolving, and longevity of civilizations. For decades, many of these variables were unknown. Today, several terms are constrained by observation. Star formation rates are measurable. The fraction of stars with planets appears high. The number of rocky worlds in habitable zones is substantial. The remaining uncertainty lies in biology. How often does life arise when conditions are favorable? On Earth, life appeared relatively quickly after conditions stabilized. Fossil evidence suggests microbial life existed at least 3.5 billion years ago, possibly earlier. Considering Earth formed 4.5 billion years ago and endured intense bombardment during its first few hundred million years, life emerged rapidly once stability allowed. This rapid appearance suggests that the transition from chemistry to biology may not be exceedingly rare. If simple life emerges readily, then microbial organisms could be widespread across the galaxy. However, the transition from simple cells to complex, multicellular organisms required billions of years on Earth. Intelligence took even longer. Probability may decrease at each step, yet time is abundant in the universe. The Milky Way is over 13 billion years old. Many stars are older than the Sun. Planets around those stars may have had billions of additional years for evolution to unfold. Statistically, even low probabilities become significant when multiplied by vast numbers. Imagine a single habitable planet where the probability of life emerging is only 1%. If billions of such planets exist, millions could host life. Probability scales with opportunity. The discovery of exoplanet atmospheres further refines this search. Instruments aboard the James Webb Space Telescope are capable of analyzing starlight passing through distant atmospheres. By studying absorption lines, scientists can detect molecules such as water vapor, carbon dioxide, methane, and potentially oxygen. Certain combinations of gases may indicate biological processes. Oxygen, for example, is highly reactive. On Earth, it persists in large quantities because photosynthetic organisms continuously replenish it. Detecting oxygen alongside methane in a distant atmosphere could suggest chemical disequilibrium, a possible biosignature. Probability transforms into observation. With each technological advance, the uncertainty narrows. Yet probability also raises a paradox. If life and intelligence are statistically likely, then why is the sky silent? This question, known as the Fermi paradox, highlights the tension between high probability and apparent absence. If intelligent civilizations are common, some should have developed technologies capable of interstellar communication or travel. And yet, no confirmed signal has been received. Possible explanations vary. Intelligent life may be rare despite microbial abundance. Civilizations may self-destruct before achieving longevity. Advanced societies may choose not to broadcast. Signals may be too faint or too brief to detect. Or perhaps humanity is simply early in the cosmic timeline. Probability does not guarantee simultaneity. Civilizations may rise and fall across millions of years. The overlap between technological societies may be small. Returning to comets, their role in probability is subtle but crucial. If water and organics are delivered efficiently to young worlds, then the initial barrier to life, chemical complexity, becomes easier to overcome. The universe may set the stage generously. Planets form. Comets deliver ingredients. Chemistry begins. From that point, natural selection drives complexity forward. Given enough time, intelligence may emerge as an adaptive strategy, the universe becoming aware of itself through biological evolution. Probability becomes destiny over cosmic timescales. The appearance of a comet in the night sky is a local event, but it symbolizes a universal process. It reminds that planetary systems are dynamic and interconnected. It suggests that Earth's history is not unique but part of a broader galactic pattern. The statistical framework now favors abundance over rarity. Life may not be exceptional. It may be expected. The deeper question shifts from does life exist elsewhere to at what stage, microbial, complex, technological? Probability does not answer that directly. But with billions of worlds and trillions of comets, the numbers hint toward a cosmos rich with possibility. And in that vast statistical ocean, Earth may be one instance among many. A single data point in a galaxy filled with experiments. Water changes everything. In the cold vacuum of space, most worlds are barren, frozen rocks, scorching deserts, crushing gas giants. But introduce liquid water and chemistry accelerates. Molecules dissolve, collide, rearrange. Complexity increases. Water is not merely a solvent, it is an engine of transformation. On Earth, life began in water. The earliest cells formed in ancient oceans nearly 4 billion years ago. Every known organism depends on it. The search for life beyond Earth, therefore, begins with a simple question. Where is the water? Comets provide part of the answer. Objects like C-2023A3 Sitchinchen Atlas are composed largely of ice. Water ice mixed with frozen gases and organic compounds. When early planets formed in the inner solar system, temperatures were too high for water to condense. Earth may have started as a relatively dry world. Cometary impacts may have changed that. Each impact delivered not only water, but also carbon-based molecules. Over millions of years, repeated bombardment could have filled basins, creating oceans. If this mechanism operated here, it may operate elsewhere. Young planetary systems are chaotic, collisions are frequent, debris is abundant. Icy bodies from outer regions can be redirected inward, striking rocky planets, forming inhabitable zones. Water becomes mobile. Beyond Earth, the solar system contains hidden oceans. Beneath the icy crust of Europa, gravitational interactions with Jupiter generate tidal heating. That heating may maintain a global subsurface ocean, more water than exists in all of Earth's seas combined. Farther out, Saturn's moon Enceladus ejects plumes of water vapor and organic molecules into space. These geysers indicate a subsurface ocean in contact with a rocky core, an environment potentially suitable for life. Even distant dwarf planets show evidence of past liquid reservoirs. Water does not require sunlight alone. It requires energy, and energy can come from tidal forces, radioactive decay, or chemical reactions. This expands the concept of habitability. A planet does not need to resemble Earth's surface. It may host oceans beneath kilometers of ice. It may orbit far from its star yet sustain internal warmth. If oceans are common in the solar system, they may be common throughout the galaxy. Exoplanet studies support this possibility. Observations reveal a category of water worlds, planets larger than Earth but less dense than rock alone would allow. These planets may possess deep global oceans hundreds of kilometers thick. Some may orbit within habitable zones. In such environments, continents may not exist. There may be no land, no mountains, no deserts, only endless sea. The chemistry of life could begin at hydrothermal vents where mineral-rich fluids interact with ocean water. On Earth, such vents teem with life independent of sunlight. Life there derives energy from chemical gradients, hydrogen sulfide reacting with oxygen, iron interacting with water. This demonstrates a critical truth: life adapts to available energy sources. The presence of water combined with chemical energy may be sufficient for biology. Comets again play a subtle but vital role. They not only deliver water but also organic precursors, molecules capable of assembling into more complex forms. Experiments simulating comet impacts show that amino acids can survive high-energy collisions under certain conditions. Impact does not always mean destruction. Sometimes it means delivery. The broader lesson is that water may be a universal mediator of life's emergence. Wherever it exists in stable form for long periods, chemistry has the opportunity to self-organize. But water alone is not enough. Stability is crucial. A planet with oceans must maintain them for hundreds of millions, perhaps billions, of years. Too much stellar radiation and oceans evaporate. Too little and they freeze permanently. Atmospheric composition regulates temperature. Magnetic fields shield against harmful radiation. Earth's stability is partly due to plate tectonics, a geological recycling system that regulates carbon dioxide levels. Without it, climate extremes could dominate. Whether similar mechanisms exist on distant worlds remains unknown. Yet the sheer number of planetary systems suggests diversity beyond imagination. Some oceans may be shallow and sunlit, others may be dark and buried beneath ice. Some may be temporary, others may endure for eons. Each ocean is a laboratory. In the vastness of the Milky Way, billions of such laboratories may exist simultaneously. The appearance of a comet in the sky is a reminder that water is not confined to planets. It is abundant in interstellar clouds. It forms naturally in cold environments where hydrogen and oxygen combine on dust grains. Water may be one of the most common molecules in the universe. If so, oceans may be the rule rather than the exception. The search for extraterrestrial life increasingly focuses on detecting water's signatures in exoplanet atmospheres and surfaces. Future missions aim to identify glints of reflected light from distant oceans, subtle hints of liquid surfaces far beyond direct imaging capabilities. A single confirmed detection of an ocean-bearing exoplanet would transform the search for life. But even before such confirmation, the trajectory of discovery is clear. Water is widespread, comets are carriers, planets are abundant, the ingredients align. Somewhere under an alien sky, waves may be crashing against unfamiliar shores or circulating silently beneath kilometers of ice. Chemical reactions may be unfolding in darkness, slowly building complexity. And if complexity persists long enough, evolution may begin its patient work. The universe may be filled not with barren worlds, but with oceans waiting for possibility to ignite. Silence can be deceptive. The night sky appears quiet, but it is saturated with signals. Radio waves from pulsars, X-rays from black holes, infrared radiation from dust clouds. The universe is constantly transmitting. The challenge is not whether signals exist. The challenge is interpretation. If life is common and intelligence occasionally emerges, then somewhere in the vastness of the Milky Way, technological civilizations may have developed communication systems. Radio waves are an obvious method. They travel at the speed of light, require relatively modest energy, and can cross interstellar distances. Humanity began leaking radio signals into space just over a century ago. Television broadcasts, radar pulses, military transmissions, all expanding outward in a growing sphere roughly 100 light years in radius. From a cosmic perspective, that bubble is tiny. The galaxy spans over 100,000 light years. The human radio footprint has barely begun. Projects dedicated to detecting extraterrestrial signals have scanned the skies for decades. The SETA Institute conducts systematic searches for narrowband radio transmissions that might indicate artificial origin. Natural astrophysical sources typically produce broadband noise. A tight, focused frequency spike could suggest technology. So far, no confirmed signal has passed rigorous verification. There have been intriguing moments, brief anomalies, unexplained bursts, but each has ultimately found a natural explanation or remained inconclusive. The famous "wow" signal of 1977, detected by the Ohio State University Radio Observatory, lasted only 72 seconds and was never repeated. One signal is not enough. Science demands repeatability. Yet silence does not imply absence. Communication requires overlap in time, in frequency choice, and technological capability. Two civilizations separated by thousands of light years must exist simultaneously and choose compatible methods of communication. That coincidence may be rare. There is also the possibility that advanced civilizations move beyond radio quickly. Humanity is already shifting toward fiber optics, tightly beamed transmissions, and encrypted communication. Leakage into space may diminish over time. Technological maturity may equal quietness. Another possibility lies in alternative methods: laser pulses, neutrino beams, gravitational waves. Detection of such signals requires technology still in development. The search is evolving. The James Webb Space Telescope and future observatories are capable of analyzing exoplanet atmospheres for biosignatures. But technosignatures, evidence of technology, represent another frontier. Artificial illumination on a planet's night side, unusual atmospheric pollutants, megastructures partially blocking starlight. Speculation often turns to the concept of a Dyson sphere, a hypothetical structure surrounding a star to capture its energy. While no confirmed examples exist, astronomers search for infrared excess that might indicate large-scale engineering. Yet the absence of visible megastructures does not eliminate intelligence. Advanced societies may prioritize sustainability over expansion. They may exist underwater, beneath planetary surfaces, or within digital environments requiring minimal energy output detectable across interstellar distances. The universe could be intelligent and discrete. Returning to comets, their role in communication is indirect but foundational. If comets distribute the ingredients for life widely, then biological evolution may be common. If biological evolution is common, intelligence may emerge repeatedly. But intelligence does not guarantee broadcast. The Fermi paradox remains: with billions of stars and potentially billions of habitable planets, why is there no obvious evidence of others? Several solutions exist. Civilizations may self-destruct through environmental collapse or technological catastrophe. They may transition into forms that do not interact physically with the galaxy in detectable ways. They may adhere to a principle of non-interference, observing but not contacting emerging civilizations. Or perhaps interstellar distances are simply too vast for practical communication. Even at light speed, a message sent from a civilization 1,000 light years away would take a millennium to arrive. A reply would require another millennium. Conversation becomes archaeology. Signals received today would represent civilizations as they were thousands of years ago. Some may no longer exist. This temporal separation complicates detection. Meanwhile, natural cosmic signals continue to surprise. Fast radio bursts, intense millisecond-long pulses were once mysterious. Some speculate about artificial origins. Further study traced many to highly magnetized neutron stars known as magnetars. Nature is capable of extraordinary phenomena. Distinguishing artificial from natural requires caution. Yet the search continues because the stakes are profound. A single confirmed artificial signal would redefine humanity's place in the cosmos. It would prove that intelligence is not unique. It would demonstrate that evolution can produce technological beings more than once. Such a discovery would not answer every question. It would raise new ones. How common are civilizations? How long do they last? Do they explore physically or remain confined to their systems? In the absence of signals, the focus broadens to biosignatures, chemical imbalances in exoplanet atmospheres, oxygen alongside methane, industrial pollutants, patterns inconsistent with geochemistry alone. Future radio arrays, more sensitive and covering broader frequency ranges, will scan millions of stars. Machine learning algorithms will sift through oceans of data, identifying anomalies that human analysts might miss. The search becomes increasingly automated. Silence, however, carries philosophical weight. Perhaps intelligence is a fleeting phase. Biological evolution may favor stability rather than expansion. Technological growth may plateau or redirect inward. Or perhaps the galaxy is filled with quiet observers, each contemplating the same question while choosing not to speak. The cosmic ocean may be teeming with life, yet acoustically calm. Part 6 teaches that absence of evidence is not evidence of absence. The search for signals is constrained by technology, time, and coincidence. Humanity has listened seriously for only a few decades, a blink compared to cosmic history. The universe may require patience. Somewhere, a distant civilization may be broadcasting right now, its signal traveling across thousands of light years, destined to arrive long after both sender and receiver have changed. The sky is not empty. It is waiting to be understood. To understand the universe, vision must expand. Every leap in discovery has followed a leap in technology. The invention of the telescope revealed moons around Jupiter and phases of Venus. Radio antennas uncovered pulsars and cosmic microwave background radiation. Space telescopes pierced dust clouds and exposed galaxies billions of light years away. The search for life beyond the solar system now depends on the next generation of instruments. The James Webb Space Telescope has already begun transforming planetary science. Operating in infrared wavelengths, it can analyze the atmospheres of distant exoplanets as starlight filters through them. Each spectrum is a chemical fingerprint: water vapor, carbon dioxide, methane, perhaps one day oxygen. Webb does not see continents or oceans directly, but it detects imbalance. Life creates imbalance. On Earth, oxygen exists in abundance because biology constantly replenishes it. Without photosynthesis, oxygen would react away in a few million years. Detecting similar atmospheric disequilibrium elsewhere would be revolutionary. Yet even Webb is only a beginning. The Vera C. Rubin Observatory will survey the entire visible sky repeatedly, detecting transient events and faint moving objects. Interstellar visitors, new comets, distant asteroids, all will be cataloged with unprecedented precision. Each discovery refines understanding of how planetary systems evolve. Future missions aim even higher. Concepts like Iluvuar and Habex, large space-based observatories, are designed to directly image Earth like planets around nearby stars. Using advanced coronagraphs or starshades to block starlight, these telescopes would isolate faint planetary light. For the first time, it may become possible to see a pale blue dot orbiting another star. Spectra from such a world could reveal oceans, clouds, perhaps seasonal changes in vegetation. The technological challenge is immense. An Earth, like planet orbiting a sun, like star, is roughly 10 billion times fainter than its host star. Blocking that glare requires extraordinary precision. But engineering evolves. Ground-based telescopes also advance. The extremely large telescope under construction in Chile will possess a mirror nearly 40 meters in diameter. Its resolving power will allow unprecedented study of exoplanet atmospheres and distant galaxies. On Earth and in space, instruments are converging toward a singular goal: detecting signs of life. Comets remain relevant in this technological era. Objects like CETA 2023-A3 Suchinshan ALAS provide opportunities to study pristine material up close. Missions similar to the European Space Agency's Rosetta demonstrate that landing on a comet and analyzing its composition is possible. Future missions may intercept interstellar objects directly. Imagine a probe launched rapidly toward a newly discovered interstellar comet, capturing images, sampling dust, measuring isotopes. Such a mission would examine material formed around another star. That would represent the first physical sample of extrasolar matter. Technology also reshapes communication searches. Next, generation radio arrays such as the Square Kilometre Array will dramatically increase sensitivity to faint signals. Billions of frequency channels can be monitored simultaneously. Artificial intelligence will scan patterns in real time. The search becomes systematic rather than sporadic. Meanwhile, planetary probes continue exploring the solar system's own ocean worlds. Missions to Europa and Enceladus aim to analyze subsurface chemistry and search for organic complexity. Discovering life within the solar system would instantly increase the probability of life elsewhere. Two independent origins within one system would imply abundance across the galaxy. The frontier extends beyond biology. Astrobiology now intersects with planetary science, chemistry, artificial intelligence, and materials science. Detecting life may require recognizing unfamiliar patterns, life not based on DNA, perhaps not even carbon, based in the traditional sense. Instrumentation must remain flexible. Spectrometers grow more sensitive. Interferometers combine light from multiple telescopes to simulate enormous apertures. Adaptive optics correct atmospheric distortion in real time. Each innovation sharpens the view. With sharper vision comes deeper perspective. The scale of the Milky Way demands patience. Even the most advanced telescope observes only a tiny fraction of stars in detail. Yet the number of observable targets grows yearly. The probability landscape becomes clearer.